Okay, this is where we left off on the first lecture. We start off with this one, just to make one more note that we were referring to in the end of the first, was we have this marked here as far as the total amount of entropy that occurred, which includes both the entropy that had happened within the system, which was the ice, and the entropy of the surroundings, which was U. And the sum total of these two gives us the total amount of entropy. Sometimes this is also referred to as the universe, the entropy of the universe. And in this case, because they are different and it was a positive value at the end, this is called an irreversible reaction, that it's going to go in one direction spontaneously for us. So it is going to occur. Another option you could have here is if we were saying that instead of being 310, that this was like just barely, they call it infinitesimally small, above 273, we could refer to this as a reversible process. But anytime you have a value where it sets up that it is greater than 0 for the reaction, in our case 2.6 positive, that is going to be considered a spontaneous reaction. Okay, let's move on over to our class notes and just take a look at some of the things we have in here. I'll go ahead and focus that in a little, and maybe even blow it up a little. Looking at some of these main concepts in here, of course, you can look at these on your own sheet. And some of the definitions I won't worry a whole lot about, just the idea that we just kind of went over the second law of thermodynamics. Third law of thermodynamics is pretty much just absolute zero. That's the main concept we're pulling out of that. And then you have some of the properties in here. So these are some things we're going to hold on to because we're going to do some of these problems together in just a moment. Looking at this one, standard molar entropies are not zero. So this is something that we can take a look at in the back of the book. I forget which appendix it is, but now we have a second one. You have all those delta H values in the back of the book. Right next door, you'll have the delta S values. And as I mentioned before, something you can take a look at is for the delta H values. Many times those are listed in, I don't know, something in kilojoules. But for the delta S values, those are almost all the time, if not always, listed in joules. So the values are much, much less small. Okay, looking at the entropies of gases, these are going to be larger than the values of liquids. So we think about, again, microstates. Gases have a lot more movement. There's more energy involved, so they have more potential for different amount of microstates. Gases have more randomness than liquids do, and liquids have more randomness than solids do, so more entropy. So you kind of interchange those as far as an idea. As far as, again, more moving parts with the material, the entropy values will increase as the molar mass goes up. More stuff, more potential for randomness. Excuse me. And then as far as the number of atoms, so you have, again, more moving parts, more potential for randomness. Gibbs we'll talk about some other time, and everything else in there we will too. So let's just take a look at the first problem we have listed here, number 15. Consider the vaporization of liquid water to steam at a pressure 1 atm. All right? Water is boiling. Water is boiling. Okay. Is this process endo or exothermic? So this is dealing with the whole delta H-ish kind of thing. You're putting energy into the water to make it boil. So I would think that is endothermic. And again, because this is a video, you can pause this at any time. So it's like, wait, don't tell me. You can just pause it and figure it out and write it down, or whatever it is you want to do on the side. Okay, and the reason for this, again, is energy is going in. All right, let's see, part B. In what temperature range is the process spontaneous? Well, if we're going to boil the water, that would imply that it needs to be above 100 degrees Celsius. And I'll say 100 degrees Celsius. Or if you want to switch that over to Kelvin, that would be 373. I'll just talk about it in Celsius. So, in what temperature range would it be a non-spontaneous? So, vaporization of liquid water to steam. It would be really weird under normal pressure conditions if this happened below 100 degrees Celsius. You can make it if you adjust the pressures. We've probably seen that in some other science class before. But normally, if it's 1 atm of pressure, it'll be really weird for water to turn to steam below 100 degrees Celsius. And of course, when is it at equilibrium? Where it's reversible, that would be right at 100 degrees Celsius. That's pretty easy, not too bad. Okay, let's keep on moving through with the notes, and we'll switch over, for me anyways, to a new sheet. All right, introduce a new concept. And that will be Gibbs, free energy. There's an interesting little story about him in the book. If you get an opportunity, go ahead and take a look at it. I believe he is the first American to get a PhD. I don't know if it's just a PhD or just PhD in like physics or something from Harvard. So Gibbs free energy. And what that is, it's kind of a weird one. I'll talk more about it here in a second. It measures the spontaneity of a reaction. Now, make sure you understand what that means. The spontaneity of a reaction has nothing to do with how fast the reaction proceeds. So, for example, rusting. Rusting will occur if you have all the conditions necessary for it to go. But the spontaneity of the reaction has nothing to do with how fast the reaction goes. It could take a really long time, but it's definitely going to happen. That's what the spontaneity means. And actually, Gibbs free energy, which we'll talk more about here in a second, delta G, it doesn't really have a life of its own. It depends on 3 different other measurements, which we'll talk about here as we move along. Okay. The more negative the value, the more spontaneous. In the forward direction. If delta G is equal to 0, the reaction is at equilibrium. So the more negative it is, it's going to move in the forward direction. And if it's at 0, it's going back and forth. It's at equilibrium. And of course, it's positive. It's still spontaneous, but it's in the reverse direction. It goes from right side towards left side. I'll add one more to this list. A reaction can drive or move from either direction. So we've pulled this information or understanding from equilibrium. It goes back and forth. So the idea of plus or minus, it's spontaneous in one way or the other. We typically, when we look at a reaction, we tend to think of it as moving from left side to right side. And we're looking at a spontaneous reaction moving from left to right normally. But we can look at it from the other direction too. If the delta G value is positive, It's spontaneous, but from the products towards the reactants. Okay, so I'll just write that in here. Products, and I'll squeeze this in. Reactions, reactants, excuse me. All right, let's look at an equation that's going to relate both these guys together. And we'll kind of derive it out. Actually, we're looking at a time here. We're about 10.5 minutes. So I'm going to go ahead and pause this, and we'll come back and we'll do lecture number 3.